So we've introduced a number of different types of potential energies, and just kind of want to take an overview of these types of energy and kind of put them together in a bigger picture. So we started off talking about kinetic energy and rest energy. And rest energy we saw was really the energy that's associated with the fact that a particle has mass. This is coming from E equals mc squared. So rest energy really is just the energy associated with the mass of a particle. The kinetic energy we've seen has to do with moving particles. Anything that's moving around that has a velocity is going to have some kinetic energy associated with it. One of the interesting things that we've come across is the fact that depending on your reference frame, you can have different kinetic energies. As we saw when we switched into center of mass reference frame, you have a relative kinetic energy relative to that center of mass point. So the kinetic energy is not a universal value. It depends on what your observation point is. And then the third class of energies that we've talked about are the potential energies. And basically this is kind of a catch-all. Anything that's not associated with the mass or the fact that the particle is moving falls into the category of potential energy. This potential energy is associated with a force, in particular a conservative force. We'll talk about that in a later section. But anytime you have some sort of force that's not a dissipative force, in other words, excluding things like air drag and friction, you typically have a potential energy associated with them. So these are the three categories of energy that all the energies we've been talking about can get classified into. The next section that we're talking about, 7.7, is dealing with the idea of power. And power really is the rate of change of energy. The book doesn't state this explicitly, but this really is what's at the heart of energy, EDT, the rate of change of energy. How quickly you're dumping energy into a system or taking it out of a system. And this equation right here, F dot V, this really only applies in the case that we have a constant force being applied to a system and moving at a constant velocity. So an example would be if we're going to take a box and lift it up from the floor to a tabletop, and we're going to apply a certain force to it, a constant force, and lift it at a constant velocity. We can calculate the power done based on those two values. This equation isn't terribly useful because most of the times the forces aren't constant or the velocities aren't constant. So this is just kind of a special case. But I do want you thinking about the idea of power. It's telling you how quickly that energy is getting dumped. So if we go back to this case of lifting the box, you can think of either lifting this box up slowly to the tabletop or lifting it up quickly. Now in both cases the change in energy is the same, but by lifting it up slowly it takes less power. Lifting up quickly takes more power.